Hey, I want to talk a little bit about DC circuits today and do some extra little problems here. Ohm's law, of course, is the big deal, but here's some other stuff that you can do for circuits that are a little more involved than just V equals IR. Wouldn't hurt to know that batteries have an internal resistance. Remember when we talked about thermodynamics and we said nothing was perfect and that you always had energy scattered about, lost, if you will. It's still there, but it's not something you can use anymore. Well, batteries are the same thing. They're not perfect either. And to represent that, very often what we'll talk about is as if they had a small internal resistance. So if this is your battery, and you know, the voltage here is 1.5 volts. What we'll imagine is that the battery itself goes and actually has a little resistor in sequence, in series with the battery itself. Okay? And that would be that internal resistance right there. A lot of times that's called little r, and you see that little r right there, lowercase r. Once you hook this up to a circuit, then it would come on around and you would have some kind of other resistance in the circuit. Maybe there's a switch and maybe there's some other stuff too, but that would be big R, the resistance of the whole circuit. This little r is what we're interested in right there. You can see it's in series with that one, so it's not hard to add it and to get the whole thing. But the trick is once current starts running in this battery, once you close the switch and it starts supplying you know, current to the rest of the circuit, there's going to be a little voltage drop across that resistor, that internal resistance of the battery. And so what you can do here is use Ohm's law, V equals IR, to calculate the voltage drop across there, and the current times the internal resistance would be the voltage drop there. So if I subtract that from the stated voltage, a lot of times this will be called V sub E, and it's never going to let me put that there. Imagine a little V there, or E there if you would. That would be V sub E. That's the stated resistance, or the EMF is often what people call it, electromotive force. That's fine. But we're subtracting the potential drop due to the internal resistance of the battery. That would give you the real, or the measured, the metered voltage. You know, so maybe my battery is 1.5 volts, and I touch it with a voltmeter and it says 1.5 volts. But then I put it to battery test, or I run it through a resistor, you know, close the circuit with it. Current starts to flow. There's going to immediately be a little drop there. You know, a couple tenths of a volt typically. Until the battery goes bad, and that's part of why the battery would go bad. Okay, that's something to think about. If a problem explicitly says there is an internal resistance of, you know, I don't know, 2 ohms or something, then really all you have to do is just draw in one more little resistor. You could do it here, you could do it in series with this one. You could just add it to that one if it's indeed in series. If you've got some stuff in parallel, then you need to do a little bit more work, but not a big deal. Just put one more resistor in there. Okay. You can add batteries in series. You know that. Every time you take, you know, unscrew the top of a flashlight and start sliding batteries in there, you're putting them in probably in series. And so we need to know how to add those up. Right here you can see that there are 3 batteries. These are car batteries, 12-volt batteries. So I've got the first 12-volt battery, the second one, and the third one. And the point they're trying to make here is that this guy is going to put 12 volts in, and he's going to put 12 volts in, and that one's going to put the 12 volts in. And together, what I need to do is to add those. So anytime batteries are in series, in a straight line like you see here, then you simply add the voltages, and we get a total of 36 volts. When you look at it, you know, electric cars and stuff, they may be running 80, 100 volts, and they've just got a bunch of batteries that are all tied in series like that to get up to that. Now you can also put batteries in parallel. Means exactly the same thing that it did when we were thinking about resistors in parallel. You remember that we drew two resistors excuse me, side by side. And this is the same kind of thing. Here's, coming from the circuit right here, this would put in 12 volts. This would also put in 12 volts, but we have to add these differently. They don't add like they do in series. They're, kind of like the resistor. We don't just get 24 there. What we actually get here is 12 volts. Now, it's really important that the batteries have the same voltage. Okay, they need to match. If they don't match, if I had 12 volts on top here and 4 volts on the bottom, this really strong battery, or relatively strong battery, would kind of backflush the weaker battery. And so you'd be wasting voltage here. You'd kill this battery really quickly. You'd probably kill that one. You'd just be wasting money and energy and everything. Okay, so they need to match, but the voltage will be the same. What you do get is it can run your device twice as long. So let's say you had an RV or a boat or something, and you wanted to go out for a long period of time, and you've got a little 12 volt light or blender or whatever it is people take in RVs. You could hook up a set like this, and then you could run your 12 volt blender, but you could do it twice as long. Okay, so that's worth knowing. Of course, you could have some mix of series and parallel. Let's say that you were using golf cart batteries, which are usually 6 volt. So I could put 2 of those in series, and that would give me 12 volts right there. Maybe I could get a whole bunch of these things for cheap somewhere, and I wanted to do that. But I need to run it longer than one golf cart battery would do, so I hook up a set of these in parallel. Okay, that gives me 12 volts. This gives me 12 volts. And when I put those together, I've got 12 volts, but I can use it twice as long. All right. Down here at the bottom, it says if you do have to worry about internal resistance, do it just like resistors in parallel. The other was resistors in series. Okay, I don't think we need to worry too much about that, but worth thinking about. I want to talk to you about Kirchhoff's rules here. Down at the bottom, you see this circuit, which is a little more involved than anything we were doing before. And this is not the most involved one we could possibly do, but it's a good place to start. So let's think about this one here. It says the sum of the currents into any point is equal to the sum of the current from that point. And they've marked a point here, point A, right there. And what we're going to do is pick a point. You can pick any point you want, but there's good reasons to pick this point over some other ones in here. Got a 12 volt battery. Here's the positive terminal of that battery. So current is going to come out. It's going to run through the resistor here to point A. So my current's coming in to that point right there. And from that point, it either goes on this way, so current is leaving right there, or it goes this way, current is leaving there. So what they're saying is that at that point, it's just 2 or 3 wires that are hooked together. There's nowhere to store voltage. There's nowhere to store current. There's nowhere to get extra current or anything. Kirchhoff's first rule there says whatever goes in has got to come back out. And they've labeled this I1, 2, and 3. There are 3 branches of the current here. You can see that, right there, 1, 2, and 3. They've actually labeled it the other way, I guess. So I'll call this one 1, and this one 2, and this one 3. It makes no difference. Pick some names and stick with them. But if you think about the current that comes in right here, it had to come through that resistor, and it had to come from over here, and it had to come from the battery, and it had to come here, right? So really, from here, let me get another color here, all the way around, we got red there, I guess we'll go with red. Whatever starts right there has no choice. There's no branch, there's no parallel line that it can take. It's got to go through the battery and through the resistor and it's going to end up right there. And so they've labeled all of that I1. All right? And you kind of got to do that first. You got to pick all the current branches. So that's the first one there. Okay, and we already said that once it gets to point A, it can either go down or it can go around. So they've labeled this one arbitrarily as I2, and the other branch is I3. And this is the first thing that you got to do these Kirchhoff problems. And to use that first rule right there, that's all you got to do. You mark off your current branches, you pick a point, and you could come in here and use that rule. The current in has to equal the current out. What comes in? Well, I1 is flowing in, and I2 and I3 are flowing out. So there's an equation right there. And that's the first thing that we're trying to do. So that would be the first equation. Now, usually you want to get this in a certain form that I'll show you, but let's just leave it right there for now. Okay? I'm going to mark that one equation 1. I think you can already guess how many equations we're looking for. I've got I1 that I don't know. I've got I2 that I don't know. I3, there's 3 unknowns here, and of course to solve that I'd have to have 3 equations. So that's where I'm headed. In this problem, I would apply the first rule one time and be done with it. In bigger, more involved problems, you might need to apply it a couple times. But honestly, anywhere else I apply rule number 1, it doesn't help me, and I'll show you why. I can pick any point that I want. For example, I could put a dot right here. And I could say, well, I got I1 coming in, and I got I1 going out. Right? I didn't involve I2 because that's from here to there. I3 is from here all the way around the outside to there. I've only got I1. I could pick that point and go I1 equals I1. Okay? And then I smack myself in the forehead and said, well, that doesn't help me. Okay? Of course that equals. I could pick any other point that I want. This one might be a good choice here. If I pick that point, I've got I2 coming in and I3 coming in and I1 going out. So if I write that equation, then I'd have I2 plus I3. Those both flow into the green point. Come on. And I1 goes out. Okay? But I'd like you to compare this to the thing that we already have. See how those are dependent equations? I don't get new information there. If I flip that around, I've got what I already have. So it doesn't help me to do this. There's nowhere else that I can pick in this problem and get more useful information. So I'd only apply that first rule one time. In other problems, there might be something else I could learn if there were more branches and it were a little more involved. This one's, we're done with rule number 1. So, rule number 2 says that when I go around a loop, and that's the critical word right there, they've drawn a couple loops here. This little blue loop starts just after the battery, and it goes around through that resistor right there. We're thinking about the current going right here, comes through that resistor. We want to let it go down I2 and back to the battery. So that's the loop that we're making right there, and we'd like to write an equation with that loop. Now, for this rule, for the loop rule, we're adding the voltages, and the sum around the loop is 0. So the sum of the voltages equals 0. Well, that makes sense. If I start right here with a certain voltage, and I add some with the battery, and I subtract some with this resistor, and I subtract some more with that resistor, I've got to get back to the same point that I started at. If I didn't, I'd be getting free electricity for nothing, or I'd be losing it into, like magic or something. Neither one of those can happen. So when I go all the way around the loop, I have to end up where I started, and that's what this rule assures us will happen. All right, I'm going to change this color because I can't see it very well, and I'm guessing you can't either. So let's see. You can start anywhere on the loop you want. You can go any direction you want. You can make any loop you want. Okay? We're trying to get two more equations, though. Here's this 12-volt battery. Why don't we start just shy of the battery? That's where I like to start. And we'll go across that. How much voltage did that add or subtract? Well, that added 12 volts. So I write down the 12. That's a plus 12. If you want to put the plus, you can. When I go from negative to positive, that increases the voltage of the circuit. I come on around some more, and I'm going down this wire, and I get to that resistor right there. That is going to burn up some electricity. That uses, I got too much going on here now. And so I'm going to draw this thing going across here like that. And when I cross that resistor, there's going to be a voltage drop. You know how much the voltage drop is. Voltage equals current times resistance. The current on this branch right here, that resistor, is part of I1. So the voltage drop right there is going to be I1 times R, which is 100 ohms. Like that. I guess I should put the unit in. But I'm going to just put it 100 I1 like that. That's my voltage drop right there. Now I don't know what I1 is yet. That's what I'm trying to find. So that's the best we can do. But that's going across that resistor on the top. We said we were going to turn right here and go down I2, following I2 across that resistor right there. That's another voltage drop. So I'm going to get minus 500 I2 by the same rationale that I did up here. Just multiply the current times the resistance, and that's equal to 0. There's equation number 2. That's some new information I didn't have before. And then, since I have 2 equations but need 3, we're going to pick one more loop and apply that rule. So what they've done here with the green is they started at the battery, went across this resistor, went straight across through that resistor, back down. There's nothing down here. There's nothing adding or subtracting voltage until I get back to the battery. So we're going to apply the loop rule again. This time the battery puts in 12 volts. That top resistor, R1, right there is 100 ohms. It's on I1. So I'd have 100 times I1. I cross point A and go across this resistor. R3 is 300 ohms, but now I'm on I3. So I need to say I3 times 300, or I can kind of put that in the order we're used to seeing it. Like that. And that would be equation number 3. Okay? I now have my 3 equations. I could solve these simultaneously and get my 3 currents, my 3 unknowns that I'm looking for right there. Alright, so I'm going to check this one off too. We actually did that one twice, once up here and twice down there. It doesn't help us to go around any more loops. It would be similar to picking a new point and doing the point rule. We would get old information. We've got all the information out of this that we can get, so now it's time to crunch it. I'm out of room, so I'm going to turn the page here. And just real quick here, here's kind of the steps that we went through. Step 1, pick a point. We pick point A because that's where all the legs of this thing came together. And just kind of, if I can find, there it is. You can see this point right there is unique in that I1, I2, and I3 all happen right there. We saw that was true down here as well, but we ended up with the same information. So either point A or down here at the bottom would be perfectly good, but not both, right? Pick a point. Anywhere else that I pick, I1 comes in and goes right back out. I3 goes in and out. Okay, no useful information. So we did that. Step 2, pick the direction that you think the current will flow in each leg and label it as I1, I2, dot, dot, dot. How many ever pieces of current you have. I would actually put that as step 1. I'm going to cross this out, and so this really should be step 1. You need to know where the current branches are, all those red lines on the picture down there. Figure all that out first, and then you can talk about your point rule and what's coming in and out of it. So let me correct that. Step 3, the current into point A equals the current out of point A. So that's actually where the current branches, I guess that's where they're pointing, you know, doing the point rule right there. There is another way that you'll see people do this. Sometimes people say the sum of the currents at a point have to equal 0. And that's kind of nice because the other rule is the sum of the voltages has to equal 0. If it's coming in, I'd call it positive. If it's going out, I'd call it negative. Here's what we got when we did it the other way, in equals out. But if I do sum of the current equals 0, then I would actually have I1 is coming in, so that would be positive. I2 is going out negative. I3 is going out negative. And it all equals 0. You can see that that turns into this, or vice versa. That's the, just subtract these two from both sides, and you'll end up right there. Actually, this is the format that we want to end it up in. So maybe it's better to do it that way anyway, but you could get this and whatever. All right, so we've got our 3 equations. How do we solve those things simultaneously? Well, there's a couple choices. One is to solve by the substitution method, and I think even from glancing at this, you can probably guess that this is not a very happy day, right? Here's those 3 equations we just cooked up. We actually had numbers in it, and I don't know why they're not in there, but you could go ahead and put your numbers in there if that makes you feel more comfortable. What we have to do, though, this is a little more general without the numbers, but it would still be that picture and not a different picture. So we see that right here is I1, I2, and I3. This equation involves all 3 variables. So if I could pick the second equation, it only has 1 and 2. If I solve this one for 2 and plug it in right there, then that would be in terms of 1. And then if I could get I3 in terms of 1, well, yeah, I could do that down here. Solve this guy for I3 in terms of I1, plug it in. You end up with this big mess here, and you do all that. And the substitution method works, and it gives you the answers down there like that. Wouldn't it be nice if there was an easier way to do that than all that? Well, there is. Okay? And if you ignore the big black box, which I'm not sure how that came to be, then this is doing this by matrices. So I've got the same 3 equations right here, and they don't have the numbers in them either for some reason. But right there, if we change this version into the second version I showed you, and then if I kind of rearrange everything here, what we did here was subtract 12 from both sides like that. So it canceled on the left, popped up on the right. This is negative, that's negative, that's negative. Everything is negative. So if I multiply the left by -1, everything over here would go positive, but I'd also have to do it here. Multiply this by -1, it would go positive. Everything would be positive, and the only other difference would be this 0R3. What I want to do in order to make a matrix out of this is have all of my I1s, all of my I2s, and all of my I3s. Well, this equation didn't have an I3, so I need to put it in there and have a place for it to sit. Okay. The same thing happens with equation number 3 here. Subtract 12, multiply through by -1, it turns into this. Put in a placeholder for I2 there, and that would be fine. Okay. Really, this isn't the way it should be written. I would put this I2 times 0. I think that would be better than 0 R2. We're trying to stack it up so that each equation, here's equation 1, equation 2, equation 3, has an I1 value and an I2 value and an I3 value, and then this would be the constants on the other side of the equal sign. Sometimes you'll even see people draw a little dotted line down like that. Say, here's my, coefficient first variable, coefficient second variable, coefficient third variable equals constant on the other side. All right, so that's the format we're trying to get this into. You can see that all that's really involved in doing that, once you've got the equations in the right format, there's a little 1 right here, a little -1 right there, and a little -1 right there, and a 0 right here. So they grab 1, -1, -1, 0, and put 1, -1, -1, 0. And then in the second one, they've got R1, R2, and 0. Again, I think that should be the other way. And right there's a 12, so there's R1, R2, 0, 12, like that. And same thing down here. Just get the coefficients of I1, 2, and 3, put it in, put your constant right there. And what we want to do once we've got this in the matrix is to transform it into, to look like this. You've got 1s on the diagonal here. This is sometimes called the identity matrix right there, when it's 1s on the diagonal, 0s everywhere else. And then there's this extra row, extra column over here like that. If I can get it in this format, remember that this first column was I1, second one I2, I3, number with an equal sign right there. So what we're really saying here is that 1I1 plus 0I2 plus 0I3 equals 0.042, and of course these don't do anything, and that 1 doesn't do anything, so I1 equals 0.042, and I2 equals 0.026, and I3 equals 16 milliamps. Like that. Okay, these are currents, so these would be in amps. Like that. Okay, so that's what we're trying to do. Now, solving systems of equations by matrices, you've got a whole bunch of different options. You could do row operations by hand. That is largely a lost art unless you've had some linear algebra somewhere. We can do it with Kramer's rule. That's not very well known anymore either, but it is a good way to do it. But probably the easiest thing is to do this with a calculator. So your calculator will chew all this up, and I'm going to do one of these here. There are those numbers that we originally had back when I don't know what happened to the numbers on those last couple screens, but right here, 1, -1, -1, and there's a 0 that's just off the screen right there. On your calculator you can scroll over and see it, but here's 100, 500, 0, and I think we had a 12 here and a 12 here. It just can't show you all of the columns at the same time. You got to get your numbers into the calculator, and then you got to have it do this thing called the RREF, and then you got to say make sure that you're doing it to the matrix that I just entered, and it will in just a flash do all that for you. So I'm gonna walk you through that. The steps are written out here. Maybe you want to screenshot that or something. I do have them on the website. There's a thing called rref.pdf that you can get on the 202-222 page, and it'll walk you through this whole thing. But let me just show you real quick how it's not that bad once you've done it a couple times. Here's my calculator, and like it says, first thing I need to do is to edit that matrix, get the numbers into my calculator. I turn it on, and matrix stuff is right there on that. It's a yellow button, so I got to hit yellow that. Okay, and this is my matrix functionality here. The names would be the names of all the matrices that I can enter into my calculator. I only need one of them. You can pick any one of these that you want. I'll go down to C here for no reason. All right. So when I hit matrix C, it says it's undefined. And so it's not going to do anything for me. I've got to put all that information into the calculator so it knows what to do. And you do that with the edit matrix over here. So I'm going to edit matrix C. And it says how many rows, how many columns do you want? And I look over here and I count the rows. 1, 2, 3. And I count the columns. 1, 2, 3, 4. So I do that. And you can see that it automatically generated all those elements for me, all the rows and columns. And I need to put the numbers in. It's as easy as going 1, enter, -1, enter, -1, enter, 0. Okay, and you see it skip over there when I hit enter. Now I'm on the second one, so I just keep going 100, enter, 500, enter, 0, 12. Just keep hitting enter. Get all your numbers in there, and it'll be fine. Okay, make sure you hit enter on that last one there. I have edited matrix C. I put all that stuff into my calculator. It wasn't that bad. I am now done editing my matrix, so I need to quit. Right there, that little yellow quit. So I hit second mode, which quits. It gets me out. All of my numbers are still in there, but it says, okay, thank you for putting some numbers in. You don't want to do anything with that, do you? And I said, well, actually, I do. So I pulled matrix back up. And I need to go over here to the math operations. So I step once to the right. And you can go either up or down. It's a little bit closer if you go up. This is the one that we're looking for, RREF. That stands for Reduced Row Echelon Form. And that's what we're trying to do. The Reduced Row Echelon Form is the thing in the box. That's what that's called. So we want to take our messy matrix with all those numbers and turn it into the reduced row echelon form with ones on the diagonal, zeros everywhere, and all the goodies right there waiting for us. Okay, so that's what we tell it to do. And the calculator goes, oh, you want to do an RREF on a matrix, huh? Wonder which matrix you want to do. And you go, oh yeah, I put those into matrix C. And it says, I would be happy to do that for you. And it puts those, and those would be the answers. The current in leg 1 of that crazy circuit is 0.041739. I'd probably chop that off and call it 42 milliamps. And I2 would be 16 milliamps, and I3 is 26 milliamps. Okay? If we round it like that, notice that, remember we had I1 flowing into point and these two flowing out. See how these two add to that one? Okay, it takes care of all of that for you. And the calculator's by far the easiest way to do that. And you're welcome to give me a call or you know, ask me, and I can show you how to do some more of these or something. We're going to do a couple more examples of this, but that's the easiest way to do it these days. All right. So let's take a look at a couple other problems, set some more of these up. This one already has all of the current directions labeled for us. Looks like this one has 2 batteries and 1, 2, 3, 4, 5 resistors. Okay. And I'm betting, since this one's a little R and that one's a little R, whereas these 3 are big R's, I'm betting that's kind of considered to be the internal resistance of that battery right there. And this one would be the internal resistance of this battery. Okay, so I've probably really got 3 resistors and 2 batteries in the circuit, and then each of the batteries has a little bit of internal resistance, only half an ohm when these are, you know, 2.5, 6, and 1.5. So not a whole lot, but enough to worry about sometimes. So we'll see what happens here. All right. I need to identify my branches. That's mostly done for us here, but I'm going to draw it out just to make sure I understand what's happening. They've called this one I2. I2 is going to start at point A, and everything that goes this way on I2, it's got to come here, it's got to go through the battery, it's got to go through the resistor, and then all the way over to here before it gets any choice, before it can do anything different. Once it gets right here, it can either go straight down or it can go to the left. All right, but if you get on this train track, you got to ride it all the way to the end right there. All right, R1 they've labeled it this way. So if I do hook a turn right there, then why won't that draw? Hello, draw over there. Here we go. Okay, so anything that comes this way has got to go all the way across. That whole thing is covered by I1. We've got I2, we got I1 marked off. Let's make sure we know where I3 goes. It starts at this point and goes down the other way, all the way to there. So there's that track. Going through the battery, going through the resistor, going through the other resistor, end up right there. The 2 points that make sense to apply the point rule would either be point A or point E. And I think you can see why. If I do the point rule at A, then I have I1 coming in. I don't know which way you like better. Positive coming in, negative going out, or in equals out. Either way works. I'll do it both ways. You can choose. I1 comes in, and I2 and I3 go out. So that would be one way to do it. Or, if I say the sum of the currents equals 0, then I would have I1 coming in, so that would be positive, and I'd have I2 going out, taking away current, subtracting I3 equals 0. Either way you want to do it is fine, but eventually I want it in that format because I'm going to put it in the matrix in that format. I1, I2, I3 equals constant, right? So I'm going to put a line under that, and you can do what you want. All right. If I do point E, I get exactly the same thing with the signs reversed, which would be like multiplying that by -1. So that's a dependent equation. No new information. Doesn't do me any good. I need to move on to a loop rule now. And I can pick any loop. I can go any direction. I can start at any point. It just doesn't matter. But there are reasons to do it one way or the other. I'm going to grab a new color here, like maybe some red would be fine. And let me just talk about why they decided to draw the arrows this way. They easily could have drawn them the other way, and that would work. But you see how the battery is this way, and the current is going from positive around to negative? If you can make these arrows match the direction of current, that makes it easier to set up all of your signs and to get it right. You can do it the other way, but if you follow the current as much as possible, it just makes life easier. Okay? So when I think about a loop, I'm going to try to follow the current too, and maybe I start right here, and I go around following I2, and then I'll come back I1 like that. Okay, well if I start in this corner at point A, and I'm on I2, and I cross a 2.5 ohm resistor, then when I do the loop rule, first time, and I say the sum of the voltages in that loop have to be equal to 0, then the first thing that happens is I cross that resistor and I lose some voltage. I'm going to have a drop right there. And so that's going to be minus 2.5, and I'm on I2. The current times the resistance would be I2 times 2.5, and I lose electricity as I go across that resistor with the current, and so it's a negative. All right, that gets me up here. Up, here's a battery. All right, so I'm going to add 18 volts. Batteries put electricity in. So there's plus 18. I go a little bit farther. Here's another resistor. That's going to cause a drop as I go with the current, in the direction of the current. And the current times the resistance. I'm still on I2, 0.5. So I need to go minus 0.5 I2. That gets me around to here. Nothing here. There's no resistors, no batteries, no resistors, no batteries. I'm turning the corner. Up, here's another resistor. Okay, that's going to be a drop. So minus 6 R. Oh, I'm sorry. Minus 6 ohms times I1. Okay, I want the the current times the resistance right there, and that's going to be minus 6 I1. So that's my equation. Now I want to clean that up. Here's a I2 term. There's another I2 term. They're both negative, so I can put those together. That's going to give me a negative 3 I2 plus 18 minus 6 I1 equals 0, and I need to get that in this same order with I1, I2, I3 equals constant. All right, so what I'm going to do is get my I1 terms out in front. That would be minus 6 I1. Need my I2 terms next. And that 18's on the wrong side. He needs to be over here, so I'm going to subtract that from both sides. And that everybody's taken care of there. Let's multiply through the whole thing by negative 1. I get 6I1 plus 3I2 equals positive 18. It just flips all the signs. Looks like I3 didn't make it into that equation, but I need a place for it. So I'm going to go 0 I3 right there. And that would be equation number 2 ready to go in my matrix. I've got equation number 1 ready to go in the matrix. And we might as well go ahead and stick those in, I guess. I'm trying to get the coefficients. So up there at the top, this guy, I got a 1, negative 1, 0. That's going to look like this. Pick another color here. I'd have 1, negative 1, 0. On the second equation, I'm going to have 6, 3, 0, 18. And I need one more equation here to finish this thing out. So I got to apply the loop rule one more time. And again, I can pick any loop. I can go in any order, any direction. It is easier to go with the current. So we did the top loop here. We went around this way. Maybe the next thing we should do would be to come around this way. Go down the bottom branch and then back across the middle. So I'm going to draw that loop right here. We'll start right here. I'm going to go down and around and back, and I got a complete loop. And right here I've got enough room to put that one in, loop rule number 2. Right there. All right, so let's see what happens. Starting at this point, there's no resistors, no batteries. Oh, here's a battery. Okay, that adds 45 volts. It's a battery, so that would be plus 45. Immediately after that, I cross a resistor. I have a drop, minus 0.5. And I got to look, see which current I'm on. I'm on I3. It's almost like being on the highway, right? Interstate 3 or something. You got to figure out which highway you're on. I'm still on I3. Here I'm going to cross another resistor, still on I3. So this would be minus 1.5 I3. Minus because it's a resistor and I'm dropping. Alright, that got me to point E. And I turn west and I go across this way, but see, now I'm on I1, right? Now I'm on a different road. And so when I cross this guy right there, I got to go minus 6I1 equals 0 right there. All right. Now I'm going to do the same steps I did up here. I'm going to get everything in the right order and all that. I'm going to try to move a little bit faster. Here's my I1s right there. It was negative. Remember, we're going to multiply through by -1. I'm out of room is the big deal here. So I'm going to write 6I1. I don't have any I2, so I got to put in a placeholder for that. I got an I3 and an I3, so we'll combine these two terms, which will give me a -2 I3, but I'm changing all the signs, so that's going to be plus 2 I3. Here's a 45. I need to subtract 45 from both sides. It comes over here and it's -45, but then I'm changing all the signs, so it's going to be a positive 45. And that's equation number 3. And I'm going to put it away for winter here, store it in a jar. Right there, 60245. Okay, we're ready to put this thing in the calculator and be done with it. So I'm going to come in here and I need to go second matrix. I need to edit a matrix. Might as well go into matrix A this time. It's already 3 by 4, so I'm just hitting enter. I need a 1. There's already a 1 there, so I'm going to hit enter. But you got to do it twice. It's almost easier just to do it again. This needs to be a -1 and a -1 and a 0 like that. Just put all the numbers in. Okay. And that last row. And I've got everybody in. So I quit. And I need to tell it to do the RREF thing. That's on the matrix menu. Step 1's to the right. And go up or down to RREF. And I got to tell it which matrix. This time I'm in matrix A. It's already on A, so I just hit enter. And there it is, ready to do it. And there's my answers. Okay, 4.75 would be the current in the first branch. I'm going to write this as a column vector here. Sometimes you'll see people switch out of the matrix version and just go I1, I2, I3 as a column vector. And you can just say I1 equals that, I2 equals this, I3 equals that. All right, 4.75. The second one here is -3.5. Well, that's certainly interesting. What's a negative sign mean in physics? It means it goes the opposite direction. This one was an 8.25 on the bottom. So what really happens is we picked I1 to be this piece across the middle. It's a positive number, which means we guessed right. It really does go from right to left. I2, which was this one right here, going up and around like that, we said it went this way, but it comes up with a negative sign. It really goes the other way. That way. Okay? We got that one backwards. It's okay. You just pick something. You guess that's the thing that made sense because the battery was pointed that way. So the current probably would go that way. Except this is only an 18-volt battery. This is a 45-volt battery. Much stronger battery. So as this current came around, most of it went this way, but some of it got jammed backwards through this battery. Right there, and that's going to kill that battery really quickly. So this is not a good circuit. All right, and that's one of the things you want to know about here. That negative sign means that it goes the opposite direction. We guessed wrong, and that's okay. The third one, I3, is 8.25. That's this way, positive number. We guessed right. That's a mighty current. That's a whole lot of current there, and that's why it's able to flush this one backwards. All right, so that's another example. Here's one right here. This is very similar to the one we just did, so I don't know that we need to do it in all its glory again, but let's at least lay out the current branches here. I'm looking at that battery and this resistor. Stuff's got to come here, and they even called I2 going that way. That would be the way I would guess because, you know, try to follow the current. And I think the current's going to go that way, that way. I don't even know what the battery is, how strong it is. So, you know, it just makes sense to guess that way and hope you're right. Down here, E2 is pointed the other way. So if it were me, I'd probably say, well, I think it's going to go that way. Now, looks like they called it the other way, right? So, again, it doesn't really matter. Just pick something and be ready to change the direction if you have to. But I would do that. Up here, there's no battery at all, so it could go either way. You'd have to look at these numbers and see what happens. They've already said it goes that way, so sure, why not? That's I1. All right, but you got to get every branch of that, and then of course you got to do the point rule. And point B would be a good candidate. Point A would be a good candidate. The others not so much. You're not going to get that much information out of it. But right there you can see that I1 is leaving, I2 is coming in, and I3 is leaving. So you'd get an equation, and that could go straight into a matrix as -1, 1, -1, 0. Okay? And so, you know, we're off and running. Next up, you do your loops. And I'd probably come in here, and with the arrows that I've drawn, I'd be sorely tempted to follow this current and follow that one. So I'd probably start anywhere I wanted to on that loop and do this one. And then I'd probably come down here and say, well, gee, I could come this way and that way. I'm following the green arrows as much as possible. You can go the opposite direction, but you have to change the signs. If I go backwards across a battery from here to there, it's not a voltage gain anymore. It's voltage gain from here to there, right? But going backwards would be a drop. And if I go backwards across a resistor, that wouldn't be a drop, it'd be a gain. So you have to think about all the signs, and to avoid that, just go with the current as much as possible. But you could lay that out, and again, I don't know what the voltages are here, so I can't even really work it. But you know, getting it set up is kind of the hard part. All right. I've got this one right here. Let me do this one real quick because I want to show you that it comes back and you could do this in an easier way. What I did with this one was I said, well, everything that starts here has got to go all the way like that. So I'm going to call that one I1. All right. When it gets to right here, this is the only battery, so the current is going to push that way. And then it can come back this way, so we'll make that I2. Just forget what they call it. All right. Or it could go on across here and turn down this way. So I'm going to call this I3, except some of the current that was here actually comes all the way over here and goes through that. So this one would be I3. This was I2. I didn't write it very well. Up here, this is actually I2 plus I3. Now, there's no resistors or batteries up there, so it doesn't really matter. But you can see that from this point, everything that goes out of here either goes on I2 or I3. And so this isn't, you know, it's probably better to not make that continuous there and there. Just call that little piece from this dot down to that dot I2. All of this can be I3, that's fine. That little piece should be I2 plus I3. There's kind of an art to doing this. But here again, when I do my point rule, I need to pick a point. Well, there's no point that involves all 1, 2, I didn't even count right, did I? This shouldn't be I2, this should actually be I3. This little piece right here, I messed this all up. And then this guy over here should be I4. Okay, I1 goes like that, I2 comes straight down, I3 is this piece right there. I4, holy cow, is all of that. So this isn't even right either. I4 right there. This up here should be I3 plus 4. Okay, sorry about that. There's all the 3 stuff. all that 4 stuff's got to go up there. Okay, and this would be I3 plus 4 as well down there. All right. The bigger these things get, the more involved they are right there. So I'm going to pick this point right here. At that point, the point rule would tell me that I1 comes in, I2 goes out, I3 and I4 go out. The only thing coming in is I1, everything else goes out. Looks like that. Okay. And then I could get set up for a loop rule. And, you know, if we're just trying to stay with the direction here, I'd probably go from here around, do I1, come down I2, and back. So right there, I'd get 6 volts in. Right there, across that resistor, that's going to be a drop. Minus I2 times R1, which was 1 kilo ohm, equals 0. Hey, that's only got one variable in it. I could go ahead and solve that one for I2. I2 times 1,000 equals 6. When I divide 6 by 1,000, I get 0.006. Okay. So if something falls out early, you don't have to go all the way through the matrix. You know, you could, and in fact, there's a way you don't even have to do Kirchhoffs with this. Actually, I'll show you in just a second. I'd like to do a loop backwards here, just to kind of let you see what happens. It's not really that bad. I want to start my next loop right here. I'm going to go around all the way around the outside like that. Okay. If I do that, I go from the positive terminal of the battery to the negative terminal of the battery. That's backwards. That's pulling 6 volts out of my circuit. The actual potential here is 6 volts higher than there. So when I go from here to there, that's a drop from this number to that number, whatever it is. The difference between here and here is 6 volts. But if I go backwards, I have to count that as a voltage drop. There's no resistors, no batteries until I get right here. And I marked I4 as this way. I'm now going backwards on I4, so I have to change the sign of that. That resistor, instead of being a drop, is now a gain. So I'd say plus the 2,000 ohms times I4. Okay, that gets me to the top of the resistor. Nothing, 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 nothing. And I'm back home, so it equals 0. That one only has one variable. I go ahead and solve that. 2,000 ohms times I4 equals 6. I4 divided by 2 would be 3, so I get a 0.003 amps right there. Okay. You could do the same thing with that that I3 there, this guy. Okay. But here's an even easier way on this one. You can't do this on the ones we were doing before. You just need to look at it and go, oh, I could do something easier. If you take your fingers and you run one of them this way, I know there's a 6 volt difference right here. If I take one finger and hold it right there at the red dot and slide the other one around, I haven't met any resistors yet, so it's still 6 volts, and 6 volts across that resistor right there means that I could use Ohm's law right there. And if I'm looking for the current, it's going to be V over R. That would be 6 volts over 1,000 ohms. And so that's going to be 0.006 amps. For that one, we called that one I2. And that's the same thing we got it when we did with the loop rule there. Okay. So sometimes, you know, you can just fall back on Ohm's law. All right, but I would not do that if you had 2 batteries. I would not do that if you had, you know, some wild stuff going on. And these aren't even wild ones. I put a couple here that make life even more interesting and stuff. We're not going to go in that deep, but I want you to know that these things do exist and that the same 2 rules work. just use the point rule, maybe more than once on these problems. Use the loop rules as many times as you need to get enough equations to solve the variables. And Kirchhoff's rule will pull you through the mud every time. All right? Even if Ohm's law won't, which it will sometimes. All right. Well, hope you enjoyed that. Thank you for your time. Have a good night. And let me know what you need, and I'll see if I can fix you up. Thank you much.